Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. Today's video kicks off our chapter on applications of exponential and logarithmic functions. We're not building models from scratch just yet. Instead, we'll focus on solving real-life equations that use preset formulas from science, finance, and everyday contexts. Let's dive into 4 examples where exponentials and logs help explain how the world works. For our first example, we're given the amount of radioactive substance left after t years is given by this equation here. So let's break that down first. When we say the amount of radioactive substance left after t years is given by, what that means is that A of t is what that sentence is. So the A here is the amount of radioactive substance left. But it is a function of t because it depends on how many years have passed. Now this A0 here is actually just A of 0. So meaning when t is equal to 0. So if t is equal to 0, then that means no time has passed. So A0 actually stands for the amount that we started with. So then the next sentence, it says if 80 grams remains from an original 120 grams, how long has the sample been decaying? So notice how here it says an original 120 grams. So that tells us this is how much we started with. So therefore, A0 is equal to 120. So then 80 grams remains, but we don't know how much time has passed. And that is what we're trying to find out. So for this equation, what we're trying to do is we're trying to solve for t. But we do know that A of t is equal to 80. So by taking these values and substituting into the original equation, we're going to get 80 is equal to 120 times e to the power of negative 0.025 t. And now to solve this, we're going to divide both sides by 120. So the left-hand side, we're going to get 2 over 3 after we simplify. And then the right-hand side is going to be e to the power of negative 0.025t. And now to bring the exponent down, we're going to take the natural log of both sides. So the left-hand side, we're going to get ln of 2 over 3. And then the right-hand side is going to be ln of e to the power of negative 0.025t. And now we can go ahead and pull the exponent down. So the left-hand side stays as ln of 2 over 3. And then the right-hand side is going to be negative 0.025t times ln of e, which is just equal to 1. And then finally, to solve for t, we can divide both sides by negative 0.025. So then we get t is equal to ln of 2 over 3 divided by negative 0.025. Okay, and if you put that into your calculator, this is going to be roughly 16.2. And since t is in years, make sure we have our unit, so that'll be years. The next example models how money grows in a bank account. So let's say you invest $5,000 into an account that compounds annually at 3.2%. So how long is it going to take for the account to grow to $8,000? And the formula that models this is given on the screen here. So just like the previous question, this notation means that P of t is the amount that is in the bank after t amount of years. Because here we're given that t is the time in years. And then similarly, P0 is just P of 0, meaning your starting principal. So just like the previous question, we're going to write down what we know. So we know that P0 is the amount of money that we started with, which is equal to 5,000. And we also know that P of t is equal to 8,000. But what we don't know is t, because we're trying to figure out how long is it going to take for the money in the account to grow to $8,000? So to solve for this, we're going to substitute the values into the original equation. So then we get 8,000 is equal to 5,000 times 1.032 to the power of t. Dividing both sides by 5,000 is going to give us 1.6 is equal to 1.032 to the power of t. Taking the natural log of both sides will give us ln of 1.6 is equal to, and then we can pull the t to the front using the power law. So that would be t times ln of 1.032. And then finally, we're going to divide both sides by ln of 1.032. So then we end up with t is equal to ln of 1.6 divided by ln of 1.032. And then to get the value of that, you're going to need a calculator. And that should work out to roughly 14.9 years. For the next example, we're talking about the relationship between the decibel level of a sound and the intensity of it. So that is given by this equation up here. So D here is equal to the decibel level. The I here is the intensity of the sound. And then the I0 is a particular value, which is 10 to the power of negative 12. So now the question is, if a sound has a decibel level of 90, what is its intensity? So again, let's write down the values that we know. So we know that D is equal to 90. And what we're solving for is the intensity. So I is the unknown that we're trying to find. So to solve for it, we're going to put in all the values that we know into the original equation. So we get 90 is equal to 10 times the log of I divided by I0, which is 10 to the power of negative 12. Dividing both sides by 10 is going to give us 9 is equal to log of I over 10 to the negative 12. Now we can use the definition of a log to convert this into an exponential equation. So that is going to give us 10 to the power of 9 is equal to I over 10 to the power of negative 12. So now multiplying both sides by 10 to the power of negative 12, we're going to end up with I is equal to 10 to the power of negative 3. So for the last example, we're comparing two sounds. So the sound of a motorcycle engine is 100 decibels, while a vacuum cleaner is 70 decibels. So how many times more intense is the motorcycle sound compared to the vacuum? So we're going to use the equation from the previous example. So let's write that down. We have that the decibel is equal to 10 times log of the intensity divided by I0, where I0 is just equal to 10 to the power of negative 12. So to find out how many times more intense is the motorcycle sound compared to the vacuum sound, we're going to need to find the intensity of each first. So let's let I sub m be the intensity of the motorcycle sound. And then let IV be the intensity of the vacuum sound. And then we're going to find each separately. So first, let's find the intensity level of the motorcycle sound. So we know that the sound of a motorcycle measures 100 decibels. So that's going to give us the equation 100 is equal to 10 times log of IM over 10 to the power of negative 12. Dividing both sides by 10 gives us 10 is equal to log of I over 10 to the power of negative 12. Converting this to an exponential equation gives us 10 to the power of 10 is equal to lost an M. These should all be IM divided by 10 to the power of negative 12. And then solving for I sub M, that is going to be 10 to the power of negative 2. Now let's go ahead and do the same thing and solve for I sub V. So the decibel level of a vacuum cleaner is 70. And that is equal to 10 times log of I sub V over 10 to the negative 12. Dividing both sides by 10 gives us 7 is equal to log of I sub V over 10 to the negative 12. Converting this to an exponential form gives us 10 to the power of 7 is equal to I sub V over 10 to the power of negative 12. And then solving for I sub V gives us 10 to the power of negative 5. And now, since the question is how many times more intense is the motorcycle sound compared to the vacuum sound, what we're going to do is we're going to take IM and divide it by IV. So meaning we're looking for the ratio between the two. So finally, we get IM divided by IV. So that's going to be 10 to the negative 2 divided by 10 to the negative 5. And that gives us 10 to the power of 3, which means it's 1,000 times more intense. So now let's do a quick recap of everything we covered in this video. We learned a few different contexts in which exponentials and logarithms apply to. But for this particular video, it didn't matter what the context of the problem was. We were given a formula or equation, and all we needed to do was substitute in our values and then use our log laws and exponential skills to solve for them. So this video was more of an appetizer to show you where exponentials and logs appear in real life. The next video is going to be more focused on developing these models from scratch. And now it is your turn to give this a try. Suppose that the population of a certain bacteria colony is modeled by this equation on the screen here, where T is the number of hours after observation began. Can you figure out how long will it take for the population to reach 10,000? And don't forget your units here. Make sure to leave your answer in the comments below and let us know if you'd like to see more content on applications of logs and exponentials in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.